I will present the work on versatile code for crack onset and propagation in complex system scenarios based on the minimization of the total energy under stress condition. This is a joint work with PhD student Karthik Ambikakumari and my colleagues Muñoz-Reja and Távara. This approach is based on the couple criterion of finite fraction mechanics proposed by Dominique Leguion 2002, which couples stress and energy criterion, which were used up to that moment just separately. Considering, for example, a simple case of a U-notch, we introduce two curves. One is, let's say, normalized tensile stress along the prospective crack path, and other is incremental and normalized incremental energy release rate along the prospective crack path. And we look for the load which leads to the intersection of these curves at the value 1, which gives us the size of the crack, finite crack at the onset, and also gives us the critical load. 10 years ago, I reformulated this approach, originally proposed by Dominique Leguion, in the form of the minimization of the total energy, which is the sum of the potential and dissipated energy, and subjected to stress condition. It can be written in terms of the minimization of the changes of the potential energy and sum of the potential energy and the change of the dissipated energy due to the formation of a new crack surface. The stress condition is that sufficiently high stresses should be applied along the prospective crack path. So in the minimization procedure, we consider just those crack surfaces which with sufficiently high stresses before the new crack onset. How does the procedure looks like? We consider, for example, a solid subjected to some load, initially possibly without no crack. Under stress criterion predicts some possible crack passes, delta A sigma. And in the next step, we bridge these possible cracks, fictitious cracks, by linear elastic spring distribution. And this allows us to furnish these fictitious cracks by damage variable. In the next step, when we apply the energy criterion, we do the minimization of the changes of the sum of the changes of the potential and dissipated energy, which results in the predicted critical crack surfaces. The introduction of the continuous distribution of springs in this fictitious crack is advantageous because this allows us to introduce damage variable D along this fictitious crack size, which leads to the minimization of the function which are separately convex. Delta P plus delta R are separately convex functionals of the displacement field and the damage variable field, which leads to a very efficient and robust numerical procedure. So imagine that we have a real crack. This is a fictitious crack predicted by the stress criterion. And we also consider a virtual crack, which moves from the zero length, up to the maximum length given by the fictitious crack length. The damage variable is 1 along the virtual crack zone and is 0 in the rest of the fictitious crack. However, first, just to fix the notation, the potential energy is basically the sum of the bulk stray energy, the stray energy along the fictitious crack predicted by the stress criterion, and minus the external work. The dissipated energy or change of dissipated energy is given by the integral of the GC times the damage variable. We can introduce to this also the mixed mode dependent fracture energy GC if we like. At the end, we minimize this functional with respect to damage variable, which, as I said, is very efficient and robust. And we, as the result of the minimization, we have the critical crack surface. However, this spring distribution application has some also challenges. We know that in the real crack tip, we have square root stress singularity. However, if we introduce ahead of the real crack, fictitious crack, it was shown in our work, but also it is probably notes from literature, that if we have a constant stiffness springs distributed along this fictitious crack, we have spurious stress singularity, square root stress singularity at the fictitious crack tip, which is not here in the situation where we have no fictitious crack. So we would like to remove this spurious stress singularity in order to have situation as much as possible similar to this one. And additionally, at the tip of the virtual crack tip, we have logarithmic stress singularity, as we showed in our recent paper. At the virtual crack tip, we need to obtain a good estimation of the energy release rate of a real crack propagating along in the head of the real crack. However, this using the constant stiffness springs, this estimation is not very good. So what we propose is to consider variable spring stiffness using this power law, using the delta length parameter between 50 or 100. This is our good experience with this. And we obtained in this way a very good estimation of the energy release rate at the crack tip. And also we remove, as we will see, the spurious singularity at the fictitious crack tip. Here is the example. This is the situation where we have just a real crack. This is the maximum principal stress distribution. And this is the maximum principal stress distribution if we use constant stiffness spring distribution along whole fictitious crack. And we see there is some singularity there, and these stress distributions are very different. However, if we use this variable stiffness spring distribution, we obtain basically the same spring distribution, stress distribution as in the case of initial perfectly bonded crack, fictitious crack faces, or if we just have real crack. So we solve these two challenges, and what we do, we apply the alternative minimization algorithm, where we minimize the change of the sum of the changes of the potential and dissipated energies. The advantage of our approach here is that we know the maximum crack advance given by the fictitious crack. So we can have several starting configurations for alternative minimization algorithm. Here are just 3 examples. This is the full, this is let's say the fully broken fictitious crack, this is partially broken, or also another partially broken. And in the end, we run basically independently alternative minimization algorithm for this starting configuration. And at the end, we just select the best minimum, which is our prediction for the crack, for the new crack advance. I will show 3 examples. In the first example, we consider, we would like to predict crack propagation, crack onset, and then subsequent propagation at the weak singularity point, which is this reentrant L-shaped corner. These red lines are let's say the cloud, the border of the cloud obtained by experimental results. And the black line is our prediction. So we obtain very good result in the crack pass. And also the critical load and the load displacement curve is in a very good agreement with the experimental results. In the other example, again, we try to predict the crack onset and subsequent propagation at one of these rectangular corner, these reentrant corners of these rectangular notches. And this is quite a known problem in concrete. Also, the previous one, but also for concrete, or for double-edge notch test from this quite famous paper by Nuru and Mohammed. The applied load is a non-proportional loading, and these are the results. If we first look on the crack pass, the gray clouds are determined by the experimental results. The blue and red are modeled, obtained by cohesive zone model, and the black line is given by our code. So we obtain even better agreement with the experimental result than the cohesive zone model. And these are the force displacement curves. And we obtained a very good agreement also with the experimental results, especially for the maximum load, for the critical load. The last example is the analysis of a crack impinging on a curved weak interface. And there is a competition there between penetration or deflection of such crack. This is the specimen. We first cut this semicircular part of the specimen, which is we introduce there an initial crack, and this semicircular part is bonded by an adhesive to this to the rest of the specimen. So we have a circular semicircular weak interface, and these the black lines are the experimental results, and in numerical results and the blue line. So we have the initially in the numerical model the small crack. After achieving the first load peak, this small crack starts to propagate, achieving the interface, which is this situation, and then it deflects, at least in this configuration, it deflects and stably propagates along the interface like the interface crack. And once it achieves the maximum second peak load, this crack interface crack kinks towards the other part of the specimen and unstably breaks the specimen. We can have a look on the how does this interface crack propagates. We can see this is the, let's say, mother crack obtained by the unstable propagation of the initially small crack, which achieved the interface and growth along the interface, and then kink and this part to the other part of the specimen. Without any special fitting, we obtain very good agreement between the size of computed size of the interface crack before kinking, 70.5 degrees, and in the experiment we obtained 16 degrees. We did several experiments, but the value of this angle was quite similar. So we obtained very good agreement with the experiment. To conclude, we developed an innovative modeling approach for crack onset and propagation prediction, which is based on the couple criterion of final fracture mechanics, which is able to successfully address a complex crack scenario, including crack interaction with interface. It was obtained by integrating Abacus Winter and Python script. We checked this code on several case studies, and we expect to explore much complex crack growth problem with this code. This code was developed in the framework of the new frac training network, financed by the European Commission, and the project Damini, financed by the Spanish Ministry of Science and University. Thank you for your attention.